If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started. All right, so we are making some good progress and we finally have reached a stage where we are looking at the most basic form of a neural network. We have this kind of architecture, which is the most classic architecture for a neural network. Let's get a little deeper and try to understand what all does it cover. So first of all, this layer that we see, these neurons in blue, these constitute the input layer. Then we have these neurons, which are beige in color, and these constitute the hidden layer, or hidden layers. We can have more than one hidden layer, but you'll have just one input layer. And finally, we have the output layer, which could contain one or more neurons, depending on the nature of problem that we are solving. This is known as the output layer. And all these neurons, if you see, have some connections. This is called a fully connected neural network. So this color coding here, like these reds and blues, do not have much of a meaning, you can say, but it is just to indicate that all the neurons of the input layer are connected to the neurons of the hidden layer. Between the two hidden layers, again, all the neurons are connected to each other. And then finally, between the final hidden layer and the output layer, again, we have all the connections. Is it mandatory to have these connections? We'll get into those details as we progress. But as of now, assume that we are talking about a fully connected neural network in its most basic form. So we started our discussions with the neurons and we've covered those over a series of tutorials. Now let's get a little deeper as to what all these neurons do. If they form a different layer, then they must be doing a different function. Let's understand that a little better. So we'll be talking about the types of neurons, and let's start talking about the input neurons represented by the blue color here. So the input neurons form the first layer of the artificial neural network. These input neurons receive the raw inputs, essentially the data. Each input neuron represents a feature. So let's say you have some data where you're talking about somebody's creditworthiness. You would be looking at maybe the features like the age of the person. You'd be looking at the income of the person. You could be looking at the credit score. You could be looking at any history of defaults and things like that. So all these features in a data would essentially be represented by each neuron in case of input layer. If you've done some amount of data pre-processing, that would be done beforehand, and then you will pass the data to the input layer. This is where the data is connected. Now, this does a one-on-one mapping between the input features and the input neurons, which means if we have 10 features in our data set, then we need 10 neurons in our artificial neural networks at the input layer. Also, there is no transformation or computation that happens at the input layer itself. So these are also called passive neurons because they just receive the inputs as is. They don't do any kind of aggregation. They don't do any kind of activation on the neurons or a transformation on the neurons based on some function. They simply receive the inputs as is. So these are passive in nature, you can say. Now let's move on to the hidden neurons, represented by this beige color. Now the hidden neurons are called so because they lie between the input layer and the output layer. So in a way, they are sandwiched. They are hidden from outside. And that's why these are called hidden neurons. Now this is where a lot of important work happens because these neurons are responsible for learning. When we talk about learning from the data, these are essentially used to learn the features from the data, the inputs from the data. They also apply necessary transformations to the data. These neurons help the neural network come up with accurate and better predictions. And this is what a typical neuron model used to talk about. So a hidden neuron does aggregation. It sums up all the weighted inputs and then passes it to an activation function. Earlier, we called it a decision function, but from now onwards, we'll call it an activation function. So basically, most of the times, these are used to apply a nonlinear transformation to the aggregated input. The output of the first hidden layer would act as the input to the next layer. And the output of the second hidden layer here would act as an input to the output layer. So this is the way network is progressing from left to right, you can say. We will be talking at length about the activation functions in the next tutorial. But as of now, we're just getting to understand the network architecture and the basic components of a network. Finally, based on what you will get as an output, we do something called as a backpropagation, which helps update the hidden neuron weights and biases to minimize the prediction errors. And there would be a separate tutorial on the backpropagation as well. Let's talk about the output neurons finally. This is where the output is being generated. This is where the predictions are finally being made. Like I said earlier, this may be one or more neurons depending on the nature of the problem that you're solving. This is just a representation for which we've shown you one neuron. It doesn't have to stick to these many number of neurons for any layer for that matter. We can try multiple variants. Output neurons provide us the final prediction or the result. If we were solving a binary classification problem, we may be looking at just one neuron or maybe two neurons. If we are solving a multi-class problem where the number of categories we are predicting are more than two, we will have those many neurons representing the output layer. And even the output neuron would do the aggregation and activation. The choice of activation function here again depends on the nature of the problem. If a binary classification problem is being solved, we could easily use a sigmoid. But if we're trying to solve a value prediction or a regression kind of a problem, we may use a different activation function, such as a linear activation function. So putting it together, we have the input neurons, the hidden neurons, and the output neurons. One important point that you might want to observe is that the neurons within a layer are never connected to each other. Neurons between the layers could be connected, but the neurons within a layer, you would not find connections between them. Also, the activation piece that we talked about would be one and the same for all the neurons in a given layer. We will not try different activation functions for different neurons. So if we choose to go with a sigmoid activation at this layer, then all these neurons will have to have the sigmoid activation. If we choose a different activation here, now let's say we choose to go with a ReLU here, then both the neurons here would have the ReLU. So now that we know about the layers, the neurons, it's time to talk about the kind of connections that we have, and that's where the weights and biases play an important role. So all these connections that you see between the neural network layers would be represented by some amount of weight. And this is what changed with perceptrons, right? We discussed this when we discussed the history of neural networks, that weights give a sense of importance for that particular connection. So let's say, for example, here, this connection is assigned a weight W1. These are called synaptic weights. Borrowing a parallel from the biological neuron where we studied synapses, these are called the synaptic weights. Likewise, we could have W2, W3. We're not putting all the notations here because it will cause a lot of clutter. But you can imagine all these connections, whether between these two layers or the last hidden layer and the output layer, all these connections will have some weights. So weights are the parameters used in the connection between neurons in a neural network. Why are we calling it a parameter? Because we don't pass this. This is learned. This is learned from the data. Remember, parameters are learned from the data and hyperparameters are set by the person conducting the experiment. So these are parameters, not to be confused with hyperparameters. We may choose how the weights are to be initialized, but we cannot exactly set the weights for these connections. So, and each weight in this would represent the strength of the connection or the importance of the connection. These are used in the computation when finding the weighted sum of input and passing it through the activation function to get the output. These WIs multiplied with the inputs XIs at different stages, summation goes as an aggregation to each layer and then is subjected to an activation function. That's what we are talking about here. And these weights do not remain static. These weights get updated as the neural network begins to learn. That's the whole advantage of having a neural network. It knows how to adjust the weights to be able to give a more favorable outcome or make less errors. So when we talk about how a neural network learns is when you'll see that these weights play a very important role in improving the performance of a neural network or improving the quality of predictions. Finally, let's talk about the biases. Now, we've just represented the biases here as constants. Of course, when we talk about doing the calculations, we will represent them as a vector. These are separate constants which are being added for each neuron. For each hidden neuron, you'll have a bias term. Even for the output neuron, you'll have a bias term. We add these parameters to make the network flexible for many inputs, as the network will work even if all the inputs are zero. So this is an important point. We talked about it while discussing perceptrons that we can assume this bias to be like a weight assigned when the input is constant, that's 1. But actually, bias is not something which is a weight. It is just a constant that's being added. The bias terms help the network capture the patterns even when all the inputs are minimal. So if we are doing a W1x1 and W2x2 and so on and so forth, adding them all, imagine if all the x1, x2, x3 inputs were 0. still you will have a bias term. If the bias was not there, then there would be no aggregation that will be happening. So this gets the network running even when the inputs are minimal. That's the advantage of bias. Generally, these are initialized with small values, but again, these are parameters, so we don't really control them. They are learned from the data just like the weights. Just like the weights, adjusting the biases also helps us improve the model performance and get our prediction closer to the actual value. So that's pretty much about what we wanted to do in this tutorial. We wanted to see how a classic neural network looked like, what are the different kind of layers that make the neural network. These layers are made up of different types of neurons and what do they do. And then we talked about the weights and biases. Of course, we have more terms to decode and more terms to learn about, which we'll continue to do in the subsequent tutorials.